So today I'm going to talk about what is angular acceleration or acceleration of a body in a circular path, like this one path. So let's discuss it. We know that there is a position vector or a radius which is taken from the center of a circle to the boundary, which is known as circumference, right? So we know that. Now I'm going to draw one vector through this point, which is velocity vector. So velocity vector is always I could say is always tangent to the this tangent to this point. This is velocity vector, or we could say that, but there is a difference between normal velocity and tangential velocity. Since this velocity vector is tangent to this point, it is also known as tangential velocity, but that will be dealing as well. Now this acceleration is acting, we know that the acceleration is always acting in the direction of velocity. So as you can see that the acceleration is acting here in the direction of the velocity, which is velocity vector, right? This is the direction of the acceleration. So yeah, so let's read it and discuss it with the with basics, right? So what is acceleration? Angular acceleration. Angular acceleration is basically change in velocity. We know that the what is formula of acceleration? Acceleration is equals to change in velocity, change in velocity divided by change in time, right? This is a linear formula, linear when we are dealing with one dimension. But if we're dealing with two dimension, or in a circular path, it usually changes as to, we know that the velocity in circular path is represented by omega, that I told you in the previous videos in the basics, and divided by change in time, that is final minus initial omega and final minus initial time. So this is angular acceleration formula. This is the formula of angular acceleration. Now we know that there are basically two type of angular acceleration. There are basically two type of angular acceleration. Oops. Okay, so the first one is instantaneous angular acceleration. Instantaneous. Uh, what's happening? Acceleration, and the second one is average acceleration. So what is instantaneous acceleration and average acceleration? Okay, let's write the formula here so it will be more easy for you to understand it. So let's take a help of this light color, like marker, vector, right? So for example, this is a alpha. And general color is same. Alpha is basically used to represent the angular acceleration, which is equals to, if we talk about instantaneous angulation, something like this: omega, change in omega into time, where time tends to 0, change in omega upon change in time, where time is equals to 0, which means the angular acceleration is acting on a body with a very short interval, for an instant of time, like a point time, right? So here the time is equals to 0, that is instantaneous acceleration. And the second is average acceleration, which is average acceleration is also same, change in velocity upon change in time, right? So it's acting upon a body that you can easily find by the final and initial acceleration, right? Velocity and then final initial time. So this is average, and this is instantaneous acceleration that is acting upon the body, right? So let's move ahead and discuss the other important factors. Let's read that. This is upon the instantaneous acceleration and the angular acceleration. So let's again move up. As you can see here, now I'm going to explain you with the help of this formula. As you can see there, this is omega. Omega basically a sign of velocity, which is change in theta, change in displacement. This is a sign of displacement. Okay, displacement. And this is a sign of omega, change in omega velocity, and change in velocity upon change in time is known as angular acceleration, right? Let's change the color. Now it's finally changed. Now we know that the velocity, we know that the dv is equals to dx upon dt, which means the change velocity is equals to displacement upon time, the rate of change of displacement. Okay, so now I'm going to do the integration here with something like this, and we know that the area under the velocity time graph is displacement, and same as for this as well, d acceleration, dA, or the stiff acceleration we're going to write here, is equals to dv upon dt, right? dv upon dt, or the area, and then I'm going to write the integration formula here with something like this, and the area under the velocity time graph give us acceleration time graph. This is acceleration, this is time graph, give us velocity. This is concept is same for the acceleration, angular acceleration as well, with right omega is equals to velocity is equals to d theta upon dt. So the area under the omega time graph give us angular displacement, and same as for this as well, के area under the alpha is equals to d omega upon dt, which means that the area under the velocity time graph, acceleration time graph give us velocity. So this concept is same for this formula, for this same formula as well. Let me increase the brightness of this laptop. Okay, so let's erase it and deal with the further information. Okay, so we know that the acceleration is a vector quantity. Acceleration is a vector quantity. This sign indicates vector quantity. So its unit is in the angular. If we talk about angle, basically there are two ways of measuring the theta. One is radian, other is degree. When radian, we don't use it more frequently. Radian is rarely used, but we use it in the physics radian, right? So this is a supplementary angle, which means supplementary unit which it does not have any dimension. Another one is angle. So the unit of acceleration is radian per second square. Angular. This is radian per second. Since sometimes radians occur and sometimes it does not occur, so the unit of acceleration is also known as 1 upon second square. This is also a unit of acceleration. 1 upon second square is also a unit of acceleration. Since I told you that this is basically a circular path, let's go for a while. Okay, let's write it. This is a center path. I have drawn a one line from center path here. Okay, let me erase it. Okay, let's do it. Okay, now this is a point here. Now I have drawn a tangent point, which is velocity, and since the acceleration is always acting in the direction of the velocity, this acceleration is always acting in the direction of velocity. This is tangent, so the acceleration is also, angular acceleration is also known as tangential acceleration. This is also tangent to a circle. It's acting in the direction of velocity. That we'll be dealing in detail as well, how it's acting and what's the phenomenon. Complete thing we'll be dealing as well. But for a while, just bear in your mind that the tangential acceleration is also known as tangential acceleration. Tangential acceleration. Just bear this thing in your mind. I will be dealing in detail as well. So let's erase it, and I'm going to explain you direction in each and everything, how it increases, what the direction of acceleration, and the complete phenomenon. Right? So let's erase it. I need a complete blank board for explaining. Just wait for a while. Yeah. So let's see with it. For this, I need two circles. One circle and other one circle. Let's use this marker. Okay, this is a center point. This is the center. Now I've drawn a line from the center. This is which is also radius and the position vector, that this is what you want to say it. So this is a velocity vector that I have drawn here. We know that the acceleration always acts in the direction of the velocity. So this is acceleration. Okay, this is acceleration, right? So what's gonna happen here is that if the velocity of a body increases, we know that the direction of the velocity can be easily known by using a right hand rule, which means that rolling your fingers from the in the anti-clockwise, and wherever your thumb will be pointing, this is a direction of the which is act. Okay, the velocity vector, angular velocity always act outside of the paper. When we gonna, this is basically